So thanks everyone for attending. I guess, well, we'll assume everybody else that is muted can hear things okay, not just Inoka and I. So today I'll be presenting the work, well, I guess a bit of my understanding and work on continuous time sigma delta modulators or ADCs in modern radio receivers, specifically for consumer applications. So I guess the outline for the talk, if this lets me slide, is that first I'm going to give a brief introduction on the place I work, who we are, which is Broadcom in Sydney, Australia. Then I'll go over some of the basics, very quick one-slider on differences between SAR ADCs and continuous time sigma delta ADCs in the context of those in modern consumer radio receivers and why the ADC is important. A little bit of in the context of continuous time sigma delta, which is what I'm interested in, will be the concerns or the issues of clock noise or phase noise in the feedback DAC of sigma delta. Sorry, it seems to be jumping slides. It must have an automatic thing. Yeah, and then talk about the subject of blockers, the signal transfer function of the sigma delta, and then a particular architecture alongside of other of my teammates worked on for products that Broadcom, I guess, developed a while ago. So just to begin with this slide, so who we are and what do we do. So most of the designers from, well, the people working in Sydney, Broadcom Sydney, are ex-Radiata or G2 Microsystems teams. The work that we do in Sydney is we design, manufacture, code, bring up, and productize high-end, state-of-the-art wireless LAN low-power consumer chips that are found in many products you'll find there for tier one manufacturers. The activities usually comprise radio frequency and analog mixed signal circuit design, the layout involved in all of those aspects for RF, analog, and mixed signal. Some of the radio and PHY system analysis for the IEEE standards, usually the state-of-the-art ones or the next generation ones. We're always working on the next thing. And digital RTL design with backend PNR work, chip assembly, and software driver for that. So I just want to put things into context. So we often speak in RF on the concept of frequency planning. There isn't much planning going on in the frequency spectrum. So you can see it's a very highly densely populated and busy structure, at least in this, for the example of the US, you can see you have a ton of standards, a ton of bandwidth that occupy different ranges of the frequency. So it's a busy spectrum from which you need to make sense of it and ensure you don't interfere with other people and other people don't interfere with you when trying to receive or transmit information. So why is the ADC a challenge or an interesting, I guess, aspect of the radio design? So the ultimate ask from a consumer low power design is the ADC, which is the analog to digital converter. What you'll find is you have your RF signal coming in, it gets amplified with a low noise amplifier. Then in a Z2IF architecture, we'll get mixed directly to DC through a synthesizer creating a reference ALO. And then once you have that down converted signal, you apply a channel selection filter, setting the bandwidth of interest within that offset to that low frequency, and then you have the analog to digital conversion. So the analog to digital converter, in order to achieve this high rate, low power, low cost radio in a crowded and segmented spectrum like you've seen in the previous slide, these tend to, the actual standards now use things like channel diversity, carrier aggregation, and spatial diversity like beamforming, meaning that you can decode several channels and aggregate them in order to create more data in the highly crowded and segmented spectrum. Or you can use spatial diversity, where you take several antennas, beamform them, and construct a more a stronger signal out of that. So you find it, at least this is contextually accurate. It was back then when I did these slides, and I should actually point out that this is borrowed, some of the materials borrowed from a workshop I gave 2016, but all the ideas are still valid today. That, at least in 3G, which is mostly also continuously valid in 4G and even more so in 5G cellular, you have many ADCs that are required to do carrier aggregation, because you need one ADC per carrier that you're decoding. And also for multiple antennas, you can have up to 16 ADCs for some of the more recent wireless standards, and you have several bandwidths. So you have, depending on different requirements for data rate, you might recruit a 10 megahertz baseband rate or a 40 megahertz baseband rate. And the choice is given depending on the application. Sometimes you want high rate, but then you want to spend more energy to decode more data. But sometimes you want low rate and you want to minimize energy. So you can make an ADC that is specific to a particular bandwidth and be energy efficient, and then a specific ADC that is designed for a wider bandwidth and more data rate. But that, if you design specific ADCs for each application, each carrier aggregation, and each MIMO application, you end up with a lot of ADCs. Another thing, I guess, the more traditional 0IF architectures are used in radios to save in the high Q external components that are used. And the reason why this is needed is because if you see this scenario, you have a signal of interest, which is what you're trying to decode in the first instance, is actually not that much higher above the noise floor. And then you have an ear blocker, which comes from another Wi-Fi channel, for instance, a neighbor that is transmitting at its maximum power, closer to your receiving device than you are receiving from the one you intend. And then there are typically fire blockers that come from either other standards or other users. So you see that when you go through the LNA, you amplify the noise floor from minus 122 to minus 54 dBm. Then you mix it down to baseband. Sorry, keeps on jumping slides. It mixed down to baseband, at which point you have a channel selection filter that helps you diminish significantly the fire blocker, but the near blocker is too close to be filtered significantly. So the ADC ends up converting not just the signal of interest, which is, needs maybe 33 dBs of dynamic range to process, but another 35 dB of blocker, which is a near blocker that if you had a high Q external device, you could filter, but because we want to save in cost and in size and weight of those devices, we accommodate that dynamic range within the ADC, means we can save in components and in cost. So that's why the ADC, even though the dynamic range required for decoding is only 30 dB, the ADC is a 70 dB ADC in order to accommodate for the fire blocker. And you want to do all of this while remain low in power, small in area, and programmable in bandwidth, because you don't want to have one ADC per bandwidth, per channel aggregation, and per MIMO multiplied all together. You want to at least reduce that the multiplication from the bandwidth. So just briefly, the two big contenders for ADCs in radios tend to be SAR ADCs or continuous time ADCs. So very, very quickly, there's a lot more to this, but a continuous time ADC is a feedback of a sampled converter, where the comparator will just take an analog sampled signal and convert it into a digitized in amplitude. If you notice in a continuous time, the sampling is inside of a feedback loop, which means aliasing terms from Nyquist theorem that will normally fold in band get attenuated by the loop, and the oversampling just makes the feedback more effective, essentially to reduce the amount of quantization noise, or the equivalent quantization of a one level quantizer can look like a multi-bit quantizer from both oversampling and noise shaping. One thing that I should notice that I probably didn't draw is that the input needs to, in a continuous time ADC, needs to drive a resistor, which is a resistive input load makes it easier. But the problem is it becomes sensitive to the DAC in many ways, feedback that mismatch if it's multi-bit, sensitive to loop delay and clock jitter. But it's a very interesting approach because you can make a one bit quantizer into a multi-bit quantizer and there's no aliasing. As opposed to the other contender, which seems to scale better with, well, would scale better with process, is a successive approximation register ADC. And the feedback, it has a feedback as well. But what it does is it produces what it does is a comparison, and then it does a binary search of where the input voltage that's been sampled lies relative to references, and you just change the reference and perform trials based on some logic, and does essentially a binary search of where the voltage sits relative to the references. The references are typically implemented from switch capacitors, and the input gets sampled at the beginning at the sampling rate, which then has to charge a sampling capacitor. Because there's a sampling capacitor switch, it means, or as a switching capacitive input, there's aliasing that is a concern, but also the fact that you have to settle quickly, and you have a driver to this capacitor that needs to charge within the sampling rate. So that makes that requirement to have a fast setting requirement. So this is a very quick idea, or at least slide explaining the two main drivers of ADCs in modern radios. So if we were to compare them side by side, so typically how we measure how good an ADC is based on its conversion efficiency. So how many joules of energy does it take to do a conversion of a step, an effective step of data conversion? So if you look at the literature, and this probably needs a little bit of updating, but essentially things are just shrinking relative to each other, but in the same sense. The SAR ADC that you can see in the literature are always below 10 femtojoules per conversion step, while the continuous time ADCs are 28 or above. Maybe they got down to 16. But the ADCs, continuous time signal ADCs standalone, always look worse than SAR ADCs on paper, at least on publications. But the thing is, the SAR ADC, as we talked about before, the previous stages need to drive the sampling cap within a time period, which is, typically say 12.5 nanoseconds, and drive 1.4 picofarads of capacitance with a swing of 0.7 peak differential. I mean, you have to also take into account the reason why the capacitor is this large is because of KT over C noise. So even though the capacitor switched, it looks like thermal noise as a resistor equivalent. And so you need to size the capacitor, otherwise your input and thermal noise contribution will be too large. So this capacitor needs to be big, and it's regardless what process and what sampling rate you have, the capacitor is always sized relative to KT over C. In this case, T is not period, is temperature, or Boltzmann equivalent, time constant times temperature. So it's a thermal equivalent. So that means it's really process independent. Doesn't matter how fast the SAR ADC gets. And again, just jumping slides with not asking. It doesn't matter how fast the SAR ADC gets. You're always limited by input sampling cap, which always means that the previous stage needs always to drive the same energy of from the buffer, needs to be able to charge that capacitor within the time period. And also because it's sampled means it has the issue of having anti-aliasing filter, no anti-aliasing filter. Which means the previous stage you need to add when you normally have a single filtering stage for the fab blocker in a continuous time because it's anti-aliasing filter robust. In the case of SAR ADC, you need an additional stage to ensure that anti-alias component doesn't fold in and degrade your in-band. So that makes it difficult, but as well, it doesn't even sufficient. You need more than 1 second, say, backward stage. You will need, in order to make this feasible, because you can't just add additional stages. What happens is if you have too many filtering stages before in a radio chain, you get frequency dependent IQ mismatch, meaning that at higher frequencies, your mismatch between the INQ channels in a 0IF radio will degrade your overall performance because it's too difficult to make a wideband 8th order stage so filter at the front of it. So what happens is you tend to have to run at 2 times the Nyquist rate that you're supposed to, just to make the filtering realizable in practice. So if you take the SAR-ADC that normally on paper looks to be a lot better, and then you add the anti-aliasing filter using some reference that I could find, even though the ADC itself takes less power, you'll notice that the anti-alias filter and driver takes more power. While in the case of the ADC for continuous time applications, there's no anti-aliasing required, the driving is easy, so the overall, the overall total power is less. And so the overall figure of merit for the ADC is more efficient overall. But again, this is only true if the ADC overcomes some of the issues that SAR-ADCs do not have. One of them is sensitivity to clock jitter. Also note that even though we shape the quantization noise to higher frequencies, we still need a digital filter to remove it, but this scales process. So if you get to latest process nodes, then that's a less power hungry application. In this case, I'm assuming 14 nanometer CMOS, which is compared to the 7 nanometers or below that people are working at. This is going to be insignificant. So why the concern of clock jitter in continuous time ADCs, and why not in SAR-ADCs? Well, in continuous time ADCs, like I said, you have a feedback loop where you put a signal in, it goes into an integrator that gets sampled, then quantized in amplitude, and that gets fed through a DAC, which is then compared with the reference, with the input voltage. So at this particular point in the feedback, you've shaped in what used to be white quantization noise, you've shaped it into the blue shape that you see here, where the quantization noise is shaped low within the signal band, but that means the energy gets shifted to high frequency. The problem is that then this high frequency is normally jitter is the product of 2 signals, which is the convolution of their spectra. So that means the input in red will convolve with, say, a jitter or phase noise spectrum in this orangey color, and then you end up with the red with some skirts along each side. This is the same as a SAR-ADC. That's no different. Your signal just becomes modulated by the jitter. But the blue curve, again, I don't know why this is jumping, and I apologize. The blue curve is another shaped noise source that is modulating with a jitter, and then becomes a noise floor in the resulting spectrum, which comes through the feedback DAC and does not get compensated. It looks as though the noise was injected at the input. So you can see that sigma delta converters have the additional problem of noise jitter modulating in band, as the quantization noise that's been shaped at higher frequencies may modulate the jitter, the clock jitter of phase noise, and then that causes a degradation. So, but this actually, in fact, largely depends on the type of feedback that you use and the jitter and the signal spectrum. So it's not just that one answer, this is worse and that's it. So if you take an example for a non-return to zero feedback DAC, where you step from one code to the next without transitioning in between, so you'll find that the overall impact of the timing error becomes a voltage error equivalent from essentially how the time gets multiplied by the height, or the width of the deviation gets converted to a height, essentially. But if you look closely at non-return to zero, you have, it's not just the height of the previous, of the current error in timing, but also of the previous. And so the equivalent error added is is essentially the 1 minus z to the minus 1 in the z domain of the jitter being multiplied in time to that. So essentially, if you do the spectra or the power spectral density of the jitter, that essentially gets added, you end up with, first is the signal component, because remember the feedback contains signal and quantization noise through a derivative. So in the case of the signal, it's just plain derivative, which is exactly the same as aperture jitter in a SAR-ADC, plus this other additional component that I've explained before, that the noise transfer function, which has high quantization noise, gets subject to derivative before it modulates the the phase noise, and that's the one of concern. So if you were to take a white noise clock jitter, applied it to a 1-bit sigma delta ADC with an autoband gain of 1.5, an oversampling ratio of 32, and a 4-fold noise transfer function, you would find that for an equivalent integrated jitter of 0.8 degrees, which is the same as 0.92 picoseconds RMS. Technical difficulties. So the overall noise floor, actually, you'll notice that even though we've shaped all this quantization noise to be below the signal, to shape the quantization noise in band to a very low level, about 10 dB worth of jitter will sit on top of that. So I don't know why this is happening. It's getting really annoying. I apologize again. I'm just going to try to remove my mouse. Hopefully, I will stop this. Yeah, so you will notice that the actual noise floor gets degraded by 10 dB above the quantization noise floor. So all that work you've done in shaping that quantization noise is 10 dB worse because of phase noise. And so that's a problem compared to a side ADC that for the same bandwidth, you end up with 8 dB below the noise floor. So a white noise affects differently. But one of the things we can do is we can look at applying a FIR in the feedback DAC. So an FIR is just a digital filter that implements a low-pass filter response, essentially. So if you were to implement a single-bit ADC, a single-bit quantizer into this FIR structure, where instead of you sum each of the individual DACs that are delayed relative to each other, and you sum them together to reconstruct an equivalent of a multi-bit. Okay, this is getting really annoying. Sorry. I'm just going to try to find a way to stop this. Maybe if I just present outside of presentation mode. Sorry. Apologies for technical difficulties. I'll just go outside of it. Okay, this should be sufficiently good for everyone, I hope. Okay. Okay, so if you apply an FIR, essentially the equivalent function that this applies is it sums the individual single bit comparator outputs and creates an equivalent of a multi-bit, which means the step size in the non-return to zero don't look as high in equivalent sense, but also applies a filtering because an FIR is essentially a low-pass filter. But what that does, it filters the noise transfer function high frequency noise before it modulates with clock jitter. It turns out that typically this is assumed to be a simple FIR when you implement this type of feedback as Potter did back in 2004, but in practice doesn't actually happen like that. And this is something that I guess it was different in the literature when I worked on this, is that you'll see that some of the timing edges, not critically important to know this, but you'll find that the timing edges will cause an error in the size of the non-return to zero curve as we showed before, but the same edge usually gets triggered by one common source, which is the clock generation. But that same edge can cause in this current pulse a negative contribution, and the next one a positive contribution. And if you look at it, you'll notice that the middle two ones, some of them get cancelled out, so you end up with a 1 minus a minus 2, which is not exactly the same expression, but essentially it's the same principle. Even though it's an FIR, you see filtering of high frequency quantization noise. So essentially what happens is with an FIR in a single bit ADC, same example we used before, same jitter, but now we've applied a 4-type FIR, a 2-type FIR, sorry, which is equivalent to a 4-type FIR, but in practice only achieves a 2-tap. You still see, even though we were 10 dB above the noise floor, now we're just 3 dB above the noise floor. So in question, you will ask yourself, what about we just use a longer FIR to reduce the jitter degradation? But then you have to watch out for stability issues. Or alternatively, you could say, well, just increase the number of DAC bits to reduce which essentially reduces the LSB contribution in this part of the equation I showed before. But if you do that, then you'll find yourself, well, I guess in the multi-bit DAC, they do have lower jitter sensitivity because it reduces the step size that modulates the jitter. But the problem is the feedback DAC requires linearization. The feedback DAC is multi-bit, and a mismatch between the DAC elements will cause distortion, essentially, equivalent to distortion of the input. You also need a low comparator offset, low offset comparator, because now the step sizes are smaller, the offset itself has to be smaller. And this results overall in large parasitics in the design. So if you want to clock this faster, the comparator starts becoming your limiting factor for how fast you can clock it. So there's been a very good review of all the different single bit FIR DACs and why they're better overall to pursue. But essentially what it comes down is area efficiency. You really want to keep it simple, no data weight averaging to remove the mismatch from the DAC in a multi-bit DAC. And remember, you want it to be efficient because you have carrier aggregation types plus the number of bandwidths there are. So you want to be the ADC to be as small and simple and compact as possible. And a single bit ADC has the advantage of being inherently linear. And it has similar loop filter linearity requirements because whatever choice of DAC you use puts a constraint on the loop filter design itself. The jitter requirements are similar to multi-bit depending on the length of FIR versus the number of multi-bit, but in general, they are comparable. And like I said, the comparator design is much smaller. You have reduced parasitics. So really there's a motivation from an area perspective in a radio where you want it to be as small ADC as possible to see if you can get a single bit FIR DAC delay compensation to work, especially for a longer number of taps. So that would bring the jitter contribution below the noise floor, at least the quantization noise floor. So one of the questions about stability, there's two ways of making a sigma delta loop. Well, a mixes of the two, but essentially there are two. One is the traditional approach is to use a nested first order loops. So instead of making a second order that could be unstable, you make a first order within another first order. So what this results in, you split essentially the single feedback into two. So that makes the inner feedback a high bandwidth compared to the outer one, which is a low noise, which looks like you've made the problem easier for you because now you have to deal with fast circuits, but they can be noisy, and slow circuits that can be low noise, which is a good thing. But the problem is you end up having to pay for power in two different places. One is to make the bandwidth high bandwidth, and the other one to make the low noise, and that's one thing. And secondly, you end up with more contributors in area. And then finally as well, because of the choice of this architecture, you end up with higher noise contribution from the active circuits. The coefficient of B1 tends to be bigger than B0, which means the H1 doesn't do a lot of attenuation of all the noise contributors from H2, meaning that you need to burn even more power to meet the same noise floor input referred in the design. And another thing is because it's an internal nested loop, they tend to, when they get overloaded, they get stuck. So you can't get out of it. You need to find, you can't overdrive them because they get stuck. So you need to find a way to reset them, which means you need to define a range over which you can operate, and that in itself reduces how usable the ADC is over that range over PVT or over process voltage or temperature conditions. So you can see that out there, there's like 47 femtojoules per convergent step for both FIR and non-FIR applications. But if you were to do in a single loop where the FIR feedback is only one, you now have to meet both low noise and high bandwidth in one loop. Now, that sounds like a challenging thing. The fact that you have a single bit makes it more aggravatedly difficult because single bit comparators rather than multi-bit means that you have to run it much faster. So it's more sensitive to delay. But overall, as a single loop, the coefficients are scaled so that A0 is bigger than A1. So contributions from anything past the first integrator get greatly attenuated. So you can save more power. One single amplifier will have to be both high bandwidth and low noise. But once that is done, then the rest is easier. But there's a challenge about, well, and it's extremely more compact because there's only one feedback, single bit, FIR DAC, and it's very small. And you can actually achieve a lower figure of merit overall, and is much more compact. And the figure of merit is because down to this A0 and A1. So yeah, you can see overall the publications tend to be, the best ones tend to be feed-forward applications, not feedback. And there's some that are a mix of the two, feed-forward, but they are just feedback architectures with a different taint on it. So the question is, how can you implement a single bit FIR DAC sigma delta converter that you can make it stable? How do you compensate for the stability? So the one way of doing this, so if you look at a single bit FIR, we have the 4-tap FIR that is equivalent to 2-tap. These additional stages take the noise transfer function, which is stable originally, and you introduce 2 unit delays, A and B, that shift the NTF away from its intended form, making it unstable most of the time. So the NTF doesn't do what it would do normally because of the loop delay. It will cause it to be unstable. But if you just were to add these are implemented simply through resistors. And if you were to add 2 feedback resistors back to the input of the comparator at different delay times, you will find that you could set those values in a way that will cancel the A and B values, and you restore the original noise transfer function. But the problem is that this has a parasitic capacitor, and these are resistors, so they need to settle fast enough to implement that coefficient of cancellation. So if you look actually for a typical, a parasitic capacitor of 10 femtos, which is quite small, and a typical feedback resistor of 40K, you end up with a rise time for the compensation path of 2.5 nanoseconds. While in this case, we are sampling at 420 picoseconds. One of that is in the gigahertz range. So we are essentially cannot settle fast enough to compensate for the delay. So that's a problem. And another additional problem is the delay, the C parasitic, is also going to add another term, which is the C term, in itself is going to cause it to become even more unstable. There have been some proposals to make to compensate for this delay, but all of them require on the gain bandwidth itself to be of those active compensation techniques to be high enough, which end up burning too much power, just to compensate for the delay and reduce the power, which is against its own merits. But essentially, just like this, doesn't look like it will work simply because the time constant, RC time constant for the settling of the compensation is not fast enough for the sampling rate we want to run this at. Well, it turns out there's a much the solution is in the source of the problem, surprisingly. So if you remember, we chose feed forward because the feed forward coefficient was bigger than the other coefficients. The coefficients are 1 over RC. So that means a bigger coefficient will mean a smaller RC. And because if you were to implement the feed-forward coefficients of the loop filter as resistors going into the same node, then the R11 resistor must be very small, or small relative to the other ones, because it's implementing a coefficient in the loop filter that is very large. What that means is that the parasitic resistance that is in parallel with the equivalent resistance that is in parallel with the parasitic capacitance is defined by the parallel combination of all the resistors. And if this is a small resistor, it will define the total resistance in parallel with that capacitor. So if you make that, because of the feed-forward architecture, having a big first stage time constant, or a large coefficient, which make a very small R11, that means your RC time constant is now actually the settling time for the feedback compensation is sufficiently fast because of the reduced load that is introduced by the time constant of R11 in parallel with the CPAR. So you can implement an effective, very high bandwidth summer with passive devices, just because the R11 is a small resistor. And that's actually, it consumes no power, no active power, and it's very compact, very high bandwidth, and it does the exceptional loop delay compensation at 2.4 gigahertz sampling rate. So it's pretty impressive. And on top of that, if you also were to add an RT1 resistor that also cancels for the effect of the CPAR, the parasitic capacitor, which also turns out to be equivalent to the delay introduced by the first integrator, which itself is, the delay is 1 over the gain bandwidth of the amplifier, which that means you can, if you were to accurately pick this RT1 value, you should be able to compensate for this CPAR, but also for any delay introduced by the first integrator. So that you can make it lower power because You don't need to be as high a gain bandwidth, so you can make it less high gain bandwidth and consume less power in the first integrator, which is the one that was supposed to be fast in the first place. So that's a really helpful thing. And in fact, you can go as high as compensating for 45% of the loop delay from the combination of the C power and the gain bandwidth of the first stage. And ends up being that, and this is typically the gain bandwidth of the first integrator tends to be 1 to 2 times the clock frequency, but in this case, you can bring it down all the way to 0.6 or 60% of the clock frequency, which is a very good thing. The question is, how robust is this? Okay, well, it looks robust. If you start doing some spreading, this is trying to say essentially that you'll find you need maybe some RC calibration to make sure that the overall absolute time constant is held together across RC skews in the process, but that's fine. That's not a difficult thing to ask or a high ask of a chip level. But we can find that when it starts to, it looks even that when you start to get to 12 tab FIR, it looks to hold itself sufficiently well, even once you include the RC cal. And essentially, this is trying to say that once you measure it, this is measuring the 2 tab, not the 12 tab, but I was just trying to make the point that 12 tab even would hold it together, but the 2 tab holds together to large variations in active circuits gain bandwidth in the first stage. But the problem isn't that simple. So if you remember, we talked about blockers before. So even though we can make the system stable and the compensation fast enough, the feed-forward architecture, which is more efficient than all the other ones, have a tendency to peak at the STF, where there's the single transfer function has a tendency to peak by 12 dB. In this particular application, it peaks by as much as 12 dB out of band. And why do we care out of band? That's where the blockers are. And if you remember, that's what we're trying to attenuate. But why does this peak happen? It's because essentially transfer function from the input to the output of the summation, which is this H of A. All the A's here, all the A coefficients are trying to slow down the H of S so that the roll-off near 0 dB crossing is not fast, because if you make it fast, it will become unstable. There's one measure of stability is how quick you cross the 0 dB point, your roll-off crosses the 0 dB point. So the zeros here are slowing down that crossing point, but this is exactly at the point that noise transfer function is coming up fast. So that means you end up with a bit of a peak out of band. So essentially, the more efficient you make the filter, the larger the STF peak, which then makes the radio receiver ADC less valuable. It kind of starts to make you think that maybe I should consider feedback altogether, because it's not just one thing, it's many. So let's just show why it's important. I forgot there was a slide about this, but if you had a blocker of 12 dB above, you essentially have to drop 12 dB the overall RX gain to accommodate for that increase in the blocker, which, if you remember, is both the in-band signal and the blocker you're trying to convert. So that means your ADC figure media effectively becomes less efficient in a 0IF receiver by the amount that the out-of-band STF is peaking. And a lot of papers out there, especially for ADCs, or at least they were for a long time, they were quoting amazing figures of media for feed-forward architectures without saying that, oh, but our STF peak is very large, which makes it completely useless for a radio. So in that specifics of radio architectures, that needs to be taken into account. So another thing which gets worse, it's not easy, is that if you increase the FIR DAC, even though we can stabilize it, the longer you make the FIR, the more peak you get out of band. So that makes essentially the feed-forward sigma delta harder for the longer FIRs, which is trying to make it more compact and more robust against the clock jitter. And it's not so bad in feed-forward architecture, in feedback architectures. So it's starting to look like the feedback actually is better than feed-forward, but we still want to hold our horses and say, well, okay, well, the question now is, but do we really need that many FIR stages in the feedback of a feed-forward? Obviously, we can't really have 12 FIR stages to bring the jitter noise below the quantization noise. But at the same time, do we really need 12? Is a question you'd be asking, because really it really becomes a trade-off between the jitter sensitivity in the clock versus the ADC conversion efficiency and its area, and essentially in a receiver. It's a really interesting confluence of requirements in the ADC. Well, asking that question, some people say, well, why don't we just filter it, the peak, and they do this through the use of feed-forward SDF coefficients. But to be honest, you end up turning it into a feedback architecture, because you end up having to process so much signal that your integrators needs to now treat or handle the quantization noise and the injected input signal. So the dynamic range of the integrator, of the first integrator, now has to accommodate more signal, so it needs to reduce its coefficient, which makes it less overall efficient in terms of how much the ability to attenuate all the other integrators' noise. It's worse because the feed forward is worse, and also the compensation gets worse, because if you remember, the compensation is determined by the size of this A0 resistor, so that means you can't clock it as fast. So it becomes a problem if you try to make it a low pass response to try to attenuate this peak, when inherently the feedback architecture already does this. It has a low pass response in itself. So we start thinking, well, this is not a good idea to try to turn a feed forward architecture into filtering one, because you might as well just use a feedback architecture. So there's questions that's being worked out there to say, what about filtering the signal before we get to the continuous time ADC? Well, you end up losing the advantage over SAR ADCs. So if you want to put an additional stage just to filter that peak, then you might as well just use a SAR ADC, because you need a SAR ADC anyway. You need an anti-aliasing filter, which is essentially what you're trying to do now, is to remove the out-of-band peaks. Instead, you put in a filter to deal with those. So might as well just use a SAR ADC if you're going to start filtering before the ADC. Well, the answer is kind of in the question. Do we actually need a filtering ADC? And the answer is no. We just want no peak. So for that, well, it's easy. Instead of targeting a filtering SDF, you can just target a flat SDF. In that case, the ADC will neither help nor hinder the radio's ability to process the signal. It will just be just as bad as the ADC would have been, and you let all the filtering be done by the stages before it. So with a flat SDF, then you end up not having to process as much signal in front of all the the output of all the integrated stages, so that those don't have to handle too much signal, which means they don't have to scale the coefficients to accommodate for the signal injected. So that means you can actually implement the whole thing with a flat SDF, and then in that particular instance, sorry, I thought it was a question for me. Anyway, so in that particular instance, the flat SDF is the way to go, because you don't have to introduce any delays, any additional signals. So you don't have to change the coefficients, and it's still been an advantageous architecture as a feed forward, but with just a flat SDF. So what the question is, actually, you still, if you make it a flat SDF and you do a 12-tap FIR, you still have the problem of, if you do a spread, the cancellation doesn't work very well. You end up with peaks up to 12 dB in a 12-tap FIR versus a 2-tap FIR. So it's still, you don't get your lunch with this one either. You can't, just making a flat SDF is becoming too sensitive with a 12-tap, but it's okay with a 2-tap. And it goes back to the question, well, why do we need a 12-tap? Well, we've assumed the jitter to be white. In practice, clock jitter isn't white. It gets integrated by an oscillator, and it turns usually into a high and low frequencies, low high frequencies. And the totally same integrated 0.8 degrees phase noise that we saw before, but if you shape it like this, there's still a total area. Its total integrated phase noise is still 0.8 degrees as it was before. And if you apply it to the same principle we did before, it used to be white, it was 3 dBs above the noise floor, and with a 2-tap FIR, it turns out that it goes down to minus 26 dB below the noise floor. So essentially, white noise or white noise equivalent makes the math much simpler, because it turns a convolution into a product, but it's actually pessimistic. In reality, even a 4-tap, which is equivalent to a 2-tap FIR, is sufficient to deal with the jitter in a typical radio. So we don't actually need a 12-tap. So that also solves that problem, which is really good, because then if you also apply a blocker that also, by the way, faults noise in band, you'll find that even that is sufficiently solid against the blocker for a realistic clock jitter. So essentially, what we've answered is, well, we wanted as much efficiency, area, and in power efficiency and in area efficiency. We know that feed-forward is the way to go, so that we can make it power efficient and area efficient. The FIR is a way to deal with the jitter, and then we compensated with these passive architecture that, because of the feed-forward implementation of the filter, of the loop filter, you end up with a small R1, which makes it fast settling time for a very nice compensation of delay implementation in a passive circuit, which is very small. And then you just add more resistors for the flat 0 dB STF. And that's a really nice compact thing. There's another, which is my colleague Jeffrey contributed towards, is the return to open FIR DAG that he used in his bandpass ADCs, also applicable in these low pass ADCs. It's really nice because it minimizes the intersymbol interference of a non-return to zero with 3 dB less thermal noise contribution than return to zero DAC for the same application. And if you do the, actually we got this manufactured, and if you look at the STF and NTF, both are solid over variation and process, and it holds the signal to noise and dynamic ratio above 64 when you change the gain bandwidth plus or minus 40% of the first stage. And the STF stays within 2 dB of below 2 dB at 14 times the bandwidth, which by then it will be easy to filter. So essentially, if you do, because it's RCs, you can actually just change the R's, scale them with frequency. And in that case, you end up with, you can use the same ADC for 10, 20, 30, and 40 megahertz by simply scaling the sampling clock in the ADC correspondingly. So 10 megahertz is 600 megahertz, 20 is 1.2, 30 is 1.8, and then it's 2.4. So you can see how the overall ADC performs. This is just so you know. And it looks tiny. It's absolutely tiny. If you look at the summation part, is the passive circuit, just the resistors, the quantizer, and the FIR is a single bit with the FIR stages, and you get all the 4 integrators, the first one being the biggest because it's lowest power and the lowest noise and fastest out of the 4. But it's essentially the smallest ADC that can be also programmed across bandwidths. And then if you just do an overall comparison of the work that was done around, well, circa 2018, it still was applicable. You can see how it compares to other works. In terms of area, that's just unbeatable, especially the fact that it does 4 different bandwidths. And in terms of figure of merit, it's just as good. If it was to be designed in one mode, because of the comparator having to be fast across all these bandwidths, it has to be a CML comparator, which meant it had to be consume more power across all bandwidths. But if you normalize to that, you still are in line with the best feed-forward ADC that was made at the time. This has gone down, but this is what's done in 40 nanometers, so it could be done better in lower process nodes. Essentially, yeah, it meets the figure of merit with no blocker degradation, because some of these ADCs, they do blocker degradation. They are feed-forward architectures with peaking, and also the smallest, which is really handy for what we're trying to do. Summary, the spatial and channel diversity requirements in the spectrum for radio receivers is pushing the for more bandwidth scalability and smaller ADCs. When you start looking at the 70 dB requirements to accommodate for both the input in bandwidth and the blocker, this ADC does so within the constraints of a real radio, the real radio clock spectrum, at the lowest figure of merit that was published at the time for a 0F receiver, and yeah, incomparable with a standalone ADC figure of merit that does not have those requirements to meet. The KT over C noise makes our ADCs less efficient because of the anti-aliasing. And even, I mean, essentially people think that because the SAR ADC is digital in nature, that it will get better in scaling and speed, but the problem always goes back to the input capacitor. And the advantages of scaling process node also are an advantage for sigma delta ADCs, where the decimator post ADC in digital is scales, but the KTC sound requirements for the SAT do not. And the most efficient architecture is definitely a feed-forward compensation. Feed-forward compensation, which if you add a flat SDF, not a low-pass filter in SDF, you'll end up with holding on to the figure of merit and the size, and still being very helpful for a 0IF. And then for FI ADAC is very efficient, requires correct blocker versus jitter compromise, but is the best DAC architecture you can have in a radio within the context of the radio. If you don't ignore the fact there's the jitter I called it. So it all combines into a nice little neat design, which has been proven in production. I think it must be in the billion units now. And just one food for thought as the last thing, and sorry to be overrunning a little bit. One of the things as well is as process at scale, the supply voltages shrink, but they don't shrink proportionally to device thresholds. And analog circuits, they don't easily or readily scale as much as digital circuits do. But one thing that does get better with process node is speed and timing, and which improves also at the same time with error reduction. So there's something you can actually have a voltage controlled ring oscillator where an input voltage at baseband will modulate the delay of number of inverter stages. And this turns out to be equivalent to a first order stream adult ADC, where the phase integration occurs first because it's continuous time phase integration, and then the sampling occurs later. And this sigma delta is back in a digital form, and it's becoming a really interesting area of research. And Professor Galton is a good reference for how these ideas came about in the first instance. And that'll be everything from me. So sorry again for overrunning. Hand over to Dinuka.
Thanks so much, Sebestian, for your very informative and interesting talk. ADCs are certainly very important components in RF systems and currently have greater demand in modern wireless systems. I've got one question from the audience, and if you have any other questions, please feel free to send them in the chat. Otherwise, you can use the raise hand notification in the toolbox. In the meanwhile, I'll go to the first question, sir.
Sure. Oh, this is in the chat. I need to. Okay. Yeah, I can see it now. So thank you. So Jeff Shee is asking, can this architecture with feed-forward and SDF peak compensation also be used in bandpass ADCs? What about quadrature bandpass ADCs? What is the most required gain bandwidth in integrated amplifier? I've actually never thought about this. Yeah, I will have to think about that. How applicable this is to bandpass ADCs. I guess you would, but you have to create a resonator equivalent of a flat SDF. And another thing you should note as well, Jeff, is that one of the things I didn't mention because of lack of time, but in a continuous time feed-forward architecture, you don't have full control over the entire SDF coefficients. You essentially have, in a fourth order, you have 4 coefficients, but the SDF has 5. So it's not a fully controlled SDF. It's a mostly controlled SDF, which, as I've shown, holds together over process. But you have to watch out if you were to implement this SDF flat response in a bandpass ADC. But it would be, yeah, in the same case, I guess, in the case of a quadrature, you have to create a complex flat SDF equivalent. So that's a really good question from someone that obviously knows about continuous time ADCs, but I haven't actually thought about it, and I guess I will think about it some more now that you have. I think it should be possible to the same principle, but again, note the fact that there's a free coefficient you don't have full control over. Yep.
There's another question. How does sigma delta ADC fit in low power RF IoT applications compared to SAR ADCs, considering the high sampling rate?
In IoT, I mean, IoT is a very wide defining term, but these days it used to be just like low power, very low rate ADCs, but that's no longer applicable. IoT now applies to things like digital TV, so dongles where they handle really high rate TV streaming services and things like that. So the term IoT, I think what the question, the person asking the question is thinking is maybe low power, low range, high range applications, for which, by the way, we have an amazing company working on in Sydney, Micro. I forgot the name. Sorry. It's not Micro. It's anyway. Someone will remind me. It's our colleagues from Sydney. Anyway, so yes. So for those applications, the applicability of sigma deltas, if the rates are not as high, the sampling rates are not as high, and the bandwidths are not as high, you don't need to settle as quickly. So that you don't have to, the capacitor size remains the same, but the sampling rate, most micros companies, sorry, the sampling rates are not as high. So that means your settling time is not as tough to meet. So then it becomes a little bit more attractive to use SAR ADCs. For low rate ADCs, SAR is definitely the way to go. But when you say IoT, you can mean anything. And in the case of high bandwidth, then the same principles have applied to radio receivers for cellular applications also apply for IoT if you are to use the more wider definition of IoT. Hopefully that answers the question. And apologies to Andy and Mike.
Thanks, Ed. There are no further questions in the chat. Does anyone have any other questions? Would like to can ask directly if you like.
I guess people are on mute. You can unmute them if you wanted to say anything.
There's another question. What is the GBW required in an amplifier?
In the case of a continuous time ADC or feed-forward architecture, it has to be above. If without compensation, it has to be typically has been 1 to twice the sampling frequency. And in the case of this design, which if you go at an early slide, I can bring it down to 0.6 or 60% of a sampling rate. So if you look at this slide, this first stage is 60% of the clock rate, and then it goes to 30%, 24%, and 12%, which is tiny. But if you didn't have compensation, then this will have to be at least 1 time the sampling rate, maybe more, 1.5 times.
Thank you. Since there are no further questions, I will hand over the session to our the vice chair of our EDS society, Bram. Bram, you can.
Thank you, Luca. First of all, we'd like to thank Sebestian for the excellent talk.
Thank you.
So we're a relatively new chapter of the IEEE, New South Wales division. So we were established only like 2 years ago, just before the outbreak of the pandemic. So it's not the best timing. So we haven't had many in-person meetings yet. But really the objective is that we bring people together from industry and academia that are working on electron or ion-based devices. So we had a seminar from one of our professors, so Martin Green, a few weeks ago, and now we have Sebestian from industry. So that's exactly what we want to see. So like the groundbreaking work that's happening in both academia and industry. So we will, if you're interested in knowing more about it, you can join us. So just look at the website of the IEEE New South Wales section, and we welcome all members, like from experienced people from industry or academia, but also students, so that we can build our community. Okay, so that's all from my side, and I want to thank Danuka for organizing this very nice seminar. And we hope that we'll have another one this year. I think we'll have another 1 or 2 planned for this year. So